I think it's time to start our webinar on vector symbolic architectures, and this is my pleasure to welcome Ali Safa from HIMEC and Catholic University Leuven in Belgium. So, Ali, without any further delay, the floor is yours, please.
Thank you, Evgeny. So yes, thanks everyone for attending today. So I'm going to give you today a talk that I also gave at the NICE conference 2023, which is about this framework that we call Support HTC, which is a framework for kind of automating the design of hyperdimensional computing circuit, but while providing a certain scalability in the sparsity of the circuit itself in order to balance accuracy and energy consumption. So, can I go to the next slide? It jumped a bit too much. Here. Okay, so first, what is hyperdimensional computing? Well, most people, of course, in this talk know it, but just to recap quickly. So, HTC is a brain-inspired method for performing machine learning tasks which reduced hardware overheads, really. And the idea can be really summarized with this kind of block diagram, where we have a certain data stream that undergoes a certain feature mapping. So the original data is projected into hypervectors that we call phi through, let's say, simple operations such as quantization, addition, element-wise XORing, and so on. And by doing these kind of operations, the input data is projected in a nonlinear way into a hyperdimensional space of dimension d. And then learning happens by, at least in the most simplest of setups, by summation or averaging of the hypervectors that correspond to each class. So I would take all the data from class 1, do the feature mapping, get their hypervectors, and then average them together to find the kind of centroid representing that class in the feature space. And so we call these kind of HTC prototypes or class centroids mu-C. And then during inference, we get query hypervectors that are basically obtained after the feature mapping of the, let's say, test data that we have. And then for doing inference, what we can do is to compare the query hypervectors to each prototype vector from, let's say, the result of the learning, and choose the class that corresponds to the highest correlation between them. And so let's say, typical way of doing this feature encoding, again, as most people here would know, is the binary spatter code, which really works as follows. You have, for example, a vector x, that is your data point that you want to encode. Each element of that vector x, you would consider it to be coded on bin bits. For example, there are integers of that depth. And so you would use a lookup table that would translate each value into a hypervector, meaning a vector of binary values that was generated randomly at the initialization of that lookup table. By doing so, you are mapping effectively this vector into an n by d kind of matrix representation, where n is the number of features in your vector and d the dimensionality of the hyperspace. And then summing is done. Before summing, in fact, you can do element-wise XORing with some, let's say, random weight matrix as well, and then, let's say, sum along the feature dimension to get the hypervector. This would be a typical, let's say, way of doing this HTC encoding. So in this work, what we want to do, now that I have given kind of a bit of the background, what we want to do is, in fact, to create a piece of software, a framework that would automate the design of these HTC, let's say, classifier circuits, as well as to train, of course, the HTC circuit to perform, let's say, various classification tasks. So we want basically a form of CAD software, a computer-aided design software, that would take a certain target data set as input, some a priori HTC circuit constraints, for example, the dimensionality of the hyperspace that you would kind of give as a specification, and then would produce for you an optimized HTC encoder circuit, as well as return for you the learned HTC prototypes, meaning the kind of centroid, let's say, vectors that represent each class in your HTC system. And of course, it would do that while respecting some objectives that you want to reach. So for example, you can say that I want to reach high accuracy while also achieving a high sparsity of my HTC circuit, for example, for saving energy and area consumption in hardware, for example. So given these objectives, this support HTC kind of framework would produce for you an optimized encoder circuit and the learned HTC prototypes. So now let's get to the first, let's say, chapter, the first, let's say, layer of the support HTC framework, which is about the design of the encoder circuit. And you will see that in this first, let's say, part, the encoder that we propose is also, let's say, has a certain novel spin, meaning that we're going to deviate from that spatter code kind of strategy and use some more top-down kind of ideas from machine learning to design our encoder. So usually when we perform classification in general, we are interested in providing a nonlinear high-dimensional mapping of the input data into a certain feature space. So here in this toy example, we have, data points in blue and in red, and the goal is to kind of separate them, classify them, but you see that in the original space that, let's say, separation line is not linear, and it's not easy to do, and so you would perform a feature mapping, so a nonlinear transformation into a higher dimensional space where hopefully you can separate the two classes using simple hyperplanes. And in fact, one of such feature mapping that is quite popular in machine learning is the so-called random Fourier feature mapping, so the RFF mapping. And the RFF mapping works as follows. This is the kind of the formula or the equation for that mapping. Given a certain vector x that you want to project into that higher dimensional space, what you would do is that you would first take the inner product of that vector x with a certain weight vector, w. Then you would multiply by a certain constant sigma, that I will explain later, and add a certain bias b. And you do that for basically d components. You see that we have, let's say, the weights and biases from 1 to d. And these weights and these biases are in fact randomly selected or randomly generated. So at the beginning, let's say, so these weights are drawn from an N01, from a standard normal distribution, and the biases are drawn from a uniform distribution between 0 and 2 pi. The sigma parameter here, in fact, sets the nonlinearity of the transform. So the larger sigma, the more this transform here will be nonlinear. So that's the random Fourier feature mapping, and it has been used a lot, for example, in the context of support vector machines to provide, let's say, a first feature encoding. So now our goal is to kind of create a HTC encoder circuit by, let's say, binarizing or heavily quantizing this random Fourier feature mapping into something that, let's say, looks more or resembles more an HTC system. So the first thing that we will do is that we will binarize or let's say threshold these cosine values to get from these floating point values into +1s and -1s and zeros that correspond more to the philosophy of HTC. So how do we do that? We basically use a threshold t, and we consider that every value of these cosines higher than that threshold t would be mapped to +1, smaller than -t would be mapped to -1, and in the middle would be mapped to 0. And here we see already two parameters, so this sigma and this t. And these two kind of additional hyperparameters here will also be automatically learned or optimized by the support HTC framework, as you will see later. But so, okay, we have been able to transform the kind of, or let's say, to heavily quantize the output of that RFF mapping into +1s and -1s and zeros, but we still have this cosine that is annoying. So how do we get rid of that cosine? Well, we remark that, in fact, we could apply this threshold of the previous slide on the arguments of the cosine, given the condition that this argument wraps around a certain constant, meaning that it exhibits the cyclic behavior that the cosine would exhibit. Of course, the threshold per se will not be the same, but qualitatively, the effect would be the same if you could apply to the argument of that cosine, given the fact that this argument would wrap around a certain constant to have that cyclic behavior. We can, in fact, achieve that cyclic behavior by computing this inner product that we saw in the random Fourier feature mapping using a cyclic accumulator with overflow underflow. So we would simply have a certain accumulator defined on BA bits, for example, as its precision. And as accumulation is taking place, well, at some point, if you exceed, let's say, the maximum, let's say, integer that bit, let's say, precision can handle, you have an overflow and you get back to 0. And so you have this cyclic behavior that would appear by using such a strategy, such a cyclic kind of accumulator with overflow. So we can use that to compute this inner product and then threshold the value of this accumulator after these recursive steps took place, really. Also, it's important to say that we saw in the random Fourier feature mapping that we had random biases. Well, here, these random biases can be, in fact, let's say, materialized through the initial value found in that accumulator that would be basically distributed from using a uniform distribution between 0 and the maximum integer value that bit precision can handle. Yeah. So, for example, if you are coding your accumulators on 8-bit, you would have values only from 0 to 255. And if you do more than 255, you would wrap around and get to 0 back, right? So now we have gotten rid of the cosines, and we have also, let's say, quantized or binarized those cosines heavily. And still, some things remains to be, let's say, binarized still here. So basically, the input x, the input vector x, and the weight matrix, the weight vector, sorry, w in the random Fourier feature mapping still need to be binarized so as to be compatible with the HTC approach. And so in this case, what we do is that we adopt the, let's say, standard strategy adopted also in the spatial code architecture, where we initialize a lookup table that associates to each possible value of each element in this x vector a hypervector that is initialized randomly, so a hypervector of binary elements, +1s and -1s. Here it's important to say that because we need to compute this inner product, we need to be consistent with the definition of the random Fourier feature mapping. We need, in fact, the translation of each element from the vector x into the hyper vector space to be statistically kind of in accordance with the value that you're trying to encode. Meaning that if you're trying to encode a value in between 0 and the maximum integer that you can represent, you would want, for example, a hypervector that has an equiprobable chance of having +1s and -1s in the hypervector that you generate. And so you want, in fact, to scale the probability of having a +1 over a -1 linearly with the value that you are trying to encode in your lookup table, so as to represent through the statistics of these hypervectors the value of x, let's say. So now that we have, let's say, used this lookup table to translate the values of x into hypervectors, we still need also to kind of binarize these weight vectors here that we see. And here what we do is that we, let's say, simply generate these weight vectors by sampling them from Bernoulli distributions with equiprobable, so equiprobability of having a -1 and +1. So this weight matrix that contains all the weight vectors, is let's say, sampled from a Bernoulli distribution. Each element is sampled from a Bernoulli distribution with probability 0.5. By doing so, we obtain, so in this kind of inner product here, we have inner product between only binary values. And so here we can do a element-wise XORing followed by an accumulation, since we are doing, in fact, multiplication of binary values. In that case, we can do a XORing instead to simplify, for example, the underlying hardware. And so this inner product would be computed as the element-wise XORing of that binary weight matrix with the input that was encoded through the lookup table. Okay, and this slide in fact summarizes the let's say the HTC encoder circuit that we use in our framework. So the input vector X is first projected into hypervectors using this lookup table. Then we have element-wise XORing with that weight matrix. Then here we deviate a bit from, for example, the spatial code approach, where we in fact do the summation with these accumulators, with these cyclic accumulators with overflow and underflow that provide a form of cyclic behavior here. And then we threshold them to get a form of thresholded version of the random Fourier feature map. And here again, I stress that the accumulation speed sigma, that sets the speed of the accumulation really, and the threshold T, that is used here, will be automatically optimized by the support HTC framework so as to balance accuracy and sparsity, in fact, in the system. So now we have reviewed the first, let's say, layer of the system, which is the encoder circuit. And now we're going to see how, in fact, we perform training, so training of the HTC system in support HTC. So, in fact, in our framework, we train the HTC system using the least square support vector machine kind of framework as well here. So we use an approach that is based on SVMs, on support vector machine, to in fact learn the class centroids, meaning the hypervector prototypes, mu-Cs. So why do we do that and how we do that? Basically, we use this optimization problem here, which is the least square support vector machine problem. It's similar to the support vector machine problem, but in fact, what you can show is that it leads to the resolution of a linear system of equation, which makes it more computationally efficient. So that's why we use the least square variant over the full variant. And the idea is as follows. We have this optimization problem where we are trying to classify the input X that are projected into the feature space through our feature encoding phi. So phi here is in fact the HTC encoder circuit that we saw in the previous section. We are trying to classify these let's say hypervectors that are produced by the encoder using in fact the SVM weight vector mu-C for each class C and the bias BC here, such that basically you classify, for example, an incoming data point as label +1 or label -1. And that's the idea. And in the case where you have multiple classes, you can simply do a one versus all classification that basically casts the problem into a capital C, let's say, subproblems that are binary. So one versus all kind of classification there. So you learn a capital C, different class prototypes, mu-C and BC. So the least square support vector machine problem is in fact quite similar to the ridge regression problem. The first term is an L2 penalty on the SVM weight, or interchangeably the HTC prototype vector, that seeks to combat overfitting. And of course, we have a second term, which is the energy minimization term, that basically is doing a linear regression with target values -1 and +1s that correspond to the labels here. And you have this gamma parameter that sets the importance between the energy minimization of the error minimization and the combating the overfitting. Now, as I said earlier, this LSSVM, this least square support vector machine problem, can be solved using a linear system of equations, in fact. So you can show that in the dual space, so when you use Lagrange optimization in the dual space, you can, in fact, learn the SVM weights or the HTC prototype vectors, mu-C, by solving this system of equation with exactly the same number of equations and unknowns. So we are trying to identify the bias BC and this vector alpha C, which are in fact the Lagrange multipliers. And we do that by simply inverting the system. So we can invert the system, for example, in Python to get BC and alpha C. And then we can find back, in fact, the HTC prototype vector mu-C that we are trying to find by linear combination of all the feature encoded data points in the training set, modulated by the Lagrange multipliers that are in fact found by solving this linear system of equation. And so the regressor matrix in that case, so the first element is 0, then you have all the labels put in a row, all the labels put in a column, and then here, of course, you have the famous Gram matrix, or the kernel matrix, where each element is in fact the inner product between the feature encoded example xi from the dataset together with the feature encoded example xj. And so you do that for all I and j's, and you get each element of that kernel matrix. And of course, you have the gamma term here again that sets the balance between overfitting and error minimization. As I said, this gamma parameter will also be automatically tuned by the support HTC optimization procedure. We have a kind of meta procedure, let's say, above the training step that I'm showing here that will address that. And then finally, when you have learned these SVM weight vectors, or interchangeably again, these HTC prototype vectors, you can simply quantize them, for example, to a certain bit precision, to B qubits, by the simple, let's say, quantization steps, to again simplify the hardware. You don't want to use floating point values. And therefore, when we get, for example, a vector X test, so a test vector that we want to classify, then what we do is that we first project it into the hyperspace using the HTC encoder circuit that we discussed in the first section. And then we look at its, let's say, correlation by taking this inner product with the HTC prototype vector of each class C. We add the bias BC of each class C, and we choose the class that maximizes this metric here, basically. So we kind of use, in fact, a similar kind of inference strategy as in the SVM case. So this is really for the training step. And before getting into the last layer of the support HTC framework, I want to draw the attention here on the importance of sparsity, so on the sparsity of the learned HTC prototypes for simplifying the hardware when you are building, let's say, HTC, let's say, hyperdimensional computing hardware in FPGA or in ASIC and so on. So let's say, for example, your HTC prototype vector μc has a lot of zeros, for example, an NZ number of zeros. Well, you see that this inner product here, there are a lot of terms that will be multiplied by zeros, and so you can simply not do the multiplication. So you can simplify computation in hardware for that matter. But it goes even further than that, because as you see in the complete encoder, so the lookup table here, and also these random weights that we had, where we were doing the element-wise XORing, in fact, every entry, let's say, that will eventually be multiplied with a zero value can be skipped, in fact, because at the end it will be multiplied by zero and not play a role in the result. And so you see how having a sparse learned HTC prototype vector allows you to not only reduce computation, but also reduce, let's say, memory utilization, reduce area, because you can, in fact, remove from hardware all the entries that will end up being multiplied by zero, therefore saving area, energy, power, and so on. Okay, and so now let's get to the, let's say, I call it the meta learning kind of layer of support HTC, which is this optimization process that uses the Nelder-Mead technique to automatically tune not only the parameters of the HTC encoder circuit, so we talked about the threshold and the speed of accumulation, but also to tune the gamma parameter that was setting the, let's say, the importance of combating overfitting when we're performing training. So, okay, so we have, as I said, this gamma, sigma, and t parameters. So combating overfitting with gamma, sigma, the speed of the accumulation, and t, the threshold. And of course, setting them is highly challenging. And what we want to do is that we want to have, again, let's say, a higher order optimization process that would learn them as well. But here, we don't really have an analytical link between how this gamma, sigma, and t parameter impact, let's say, our objective, so what we want to achieve with our system. And so, for that reason, we resolved to a black box technique called the Nölder-Mead kind of approach, also called the simplex approach. And so this approach, I will detail it in the next slide later, but the idea is, in fact, that it tries to extrapolate the behavior of that cost landscape and simply move downhill again. But it does it in a black box manner, meaning by trying to extrapolate the cost landscape, by probing the cost landscape as it goes along. So as the cost function of this optimization problem, we not only want to maximize accuracy, but as I said, sparsity is important. So we want to also maximize sparsity, the sparsity of the hypervector centroids, so the SVM weight, if you want. And so, of course, okay, in this case, we want to have a cost that we minimize. So that's why we put a minus sign in front of it. And so we want to minimize this quantity, but in reality, we want to maximize accuracy and sparsity. And we have this lambda parameter that sets the balance between how much you put importance to maximizing sparsity and how much you put importance to maximizing accuracy. So it sets that trade-off. And the system will work as follows. So given an initial set of parameters, gamma, sigma, and t, the HTC train test procedure can take place. And then we can compute the cost, so the accuracy and sparsity combined, give it to the Nölder-Mead algorithm, which will then use the cost associated to each set of initial parameter to propose a new set of parameter, gamma, sigma, and t, that we will then try again with the train test procedure, compute their cost, and so on. And through this iteration, the gamma and sigma and t parameters will be fine-tuned so as to minimize this cost function, meaning to maximize this balance between accuracy and sparsity. In this slide, I detail a bit more how the Nölder-Mead optimization process works. So as I said, it's a heuristical optimization method. So given a certain set of initial points, for example, in this triangle that is moving here, what it does is that it tries to extrapolate the behavior of the cost function locally within that simplex, within that kind of, red triangle that you have here. And as it extrapolates the behavior of the loss landscape, it tries to move downhill according to that. And yeah, so it starts, as I said, from a certain set of initial points. So you need to start with, for example, NS number of gamma, sigma, and t drawn randomly. That would cover a large portion of the loss landscape. And then little by little, the Nölder-Mead will propose to you a new set of parameters, gamma, sigma, and t new at each iteration that you can try and little by little converge to a local optimum. So if you want more information, of course, there's the original paper listed here. So, okay, now we have seen the last, let's say, layer of the support HTC framework. Now let's dive into the experimental result here. So as a first experiment, we use the Wisconsin breast cancer detection dataset. Here, the goal is to, let's say, detect the presence of cancer in biomeasurements. And what we do here is that we, let's say, specify a hypervector dimensionality of 1,000, these accumulator bit width, and so this accumulator, cyclic accumulator that we have, we, let's say, restrict them to 8 bits, and we use as precision for the HTC prototype vectors, meaning the SVM weights, 4 bits as their precision. And what we do is that we, in fact, sweep lambda, so that lambda parameter that sets the balance between how much you want to maximize accuracy and how much you want to maximize sparsity. So we sweep lambda in order to find this kind of Pareto front, this kind of trade-off front between accuracy and HTC prototype sparsity. So what you see is that this is kind of the result, let's say, provided by support HTC. It provides you these blue kind of dots that you see, these blue crosses that you see. And each of these blue crosses is a possible HTC design, in fact. It's a possible design with its associated HTC prototype vector, meaning the result of the learning process. The orange line is just an interpolation here. And what you see is that indeed, as you, let's say, specify more sparsity in your system, accuracy would degrade little by little. But this is interesting because then, let's say, for example, in some application, you want to achieve, you have a specification, you need to achieve more than, for example, 90%. Well, then you can perhaps achieve that accuracy, but while tapping into higher sparsities and drastically, in fact, simplify your hardware. So that's the result of that kind of computer-aided design software that we have, that we call support HTC. We also did some experiments with the cardiac arrhythmia dataset. It is more challenging as it contains, in fact, missing values across the biosignal measurements, and we simply, in fact, replace the missing values with 0, which is not the most optimal thing to do. Here we chose a dimensional D of 5,000. The rest we kept the same. And what we see here again is kind of a similar trend in the sense that as you specify higher sparsities, you have generally a loss in accuracy. But it's interesting to kind of compare the performance of what support HTC is able to give us to, let's say, baseline HTC systems that are using, for example, the spatial code approach. For that, we use, in fact, an open source implementation recently published in this work, and where we see that indeed the support HTC framework reaches a higher accuracy than that base kind of baseline system. But more importantly, while providing this scalability in the sparsity of the system. So it really allows you to, let's say, get this kind of trade-off curves where you can trade off between accuracy and sparsity, and therefore, you know, basically tailor or choose a certain design based on your hardware specification, for example. Okay, so I'm already at the conclusion. So in this presentation, we presented our developments towards a form of automated HTC circuit design framework that can trade off classification accuracy and hardware overheads, and through the control of the sparsity of the system. We, in fact, let's say, derived the encoder circuit of that support HTC framework through the random Fourier feature mapping, which differs, let's say, from the conventional spatial code approach, due to its use, in fact, of these overflowing and underflowing accumulators and followed by thresholding. And also, quite crucially, instead of the conventional kind of HTC training techniques where, let's say, we would average or bundle together hypervectors, here we really used this least square support vector machine method to train, in fact, the HTC circuit. And we also had our Nelder-Mead optimization algorithm on top of it to fine-tune the circuit parameters and the hyperparameter of the training. Yeah, so as future work, we really plan to explore sort of better ways to approximate that random Fourier feature mapping. We feel that perhaps there are better ways to do it, and some recent papers also indicate that. And for, let's say, more information, you can also find one of our papers describing the work presented in this presentation in more depth. So if you're interested, you can also, of course, take a look at that paper. So thanks a lot for listening to this presentation, and of course, open to any question you might have.
Thank you very much, Ali, for the great talk. So now we have time for questions. Please unmute yourself and speak up. Let's see. Okay.
So
yeah, please.
Yeah, thanks for the very clear talk, Ali. So I'm just wondering, I mean, how does this compare? I mean, of course, classification is kind of a very standard problem. Where do you see the advantages to just classic approaches to solve the same data sets, you know, the classification of the same data sets?
Yeah, I would say that really the main, let's say, selling point is the hardware friendliness of it. So yeah, I personally also work like kind of closely with the hardware side. So we are really kind of concerned in building hardware that are extremely simple for example, using only binary kind of representations, spiking neural networks, things like that. And here in this case, for example, compared to a normal support vector machine where you would have, of course, floating point values for the weights and so on, here you don't need floating point weights. And so this kind of circuits could be potentially very simply implemented in FPGA. You know? So this is really the kind of attraction that we have here. So
what was the measure of sparsity that you used in
Yeah. That's a good question. So indeed, as you see, they go from, let's say, 0 to 1. The measure of sparsity is in fact the number of zeros that you have in the HTC prototype vector. So the prototype vector here, but divided by the length. So
I see. So it's an L0 sparsity that you use in your measure of sparsity.
Yeah. So a sparsity of 1 would mean that everything is 0. A sparsity of 0 would mean that everything is not 0. Yeah.
And then in your final table with the with the results, with the experimental results, what sparsity did you use there? And I mean, is this then is kind of the accuracy that you get, is this on par with what I guess it's worse probably what people achieve that have almost infinite precision?
Yeah. So the accuracy that we report here in this table is, of course, the maximum accuracy that the support HTC provides. The maximum.
So with low sparseness then.
Well, it's funny because it's not necessarily always at the lowest
right.
sparsity. Yeah? So you see that, for example, here, it goes up a bit.
Actually, why does this curve come up first?
Yeah, that's because when you put lambda, so lambda, which is this thing that sets the balance between accuracy and sparsity, to 0, that's where you are maximizing accuracy. But it turns out that if you just want to maximize accuracy, you get naturally a certain sparsity in the hypervector itself. And the sparsity comes from the fact that the weights are quantized. So don't forget that we have a quantization happening. So which would push some weights to 0. And so naturally you have a sparsity already in there. Now, if you force less sparsity, so you might want to make it more dense, then it corresponds to an optimization problem where you are not optimizing only for maximizing accuracy. And that's why the accuracy is lower, in fact. So to be very complete in my answer, this part of the front, this part of the plots don't correspond to the so-called Pareto front. The Pareto front really starts from that.
Okay, yes. Thank you.
Thank you.
Tony, you were next.
Yeah. Thanks for the interesting talk, Ali. One question I had, something I wasn't quite sure I understood properly. It sounded like you were saying that higher levels of sparsity resulted in simpler hardware. And I'm not seeing how that's the case. I can see how if you have like 80% are zeros, then you need to compute less things in your hardware, but it's not making the hardware any simpler, is it? In terms of how the hardware is laid out and that kind of thing.
Yeah, that's a very good point. So indeed, so if you have, for example, just a processor, in that case, yes, you have zeros, you can perhaps skip computation. There are methods to do that. But here in this case, we are trying to target, let's say, the physical implementation of that HTC, for example, in FPGA, so in a massively parallel manner. We're not doing a form of sequential kind of implementation like a processor would do. Rather, we would do a massively parallel implementation of it. So let's say, for example, let's take again this example. We have this lookup table here. We have the weights here, and we do this element-wise XORing between the 1s and -1s here, the 1s and -1s here, and then we sum them and get the resulting, let's say, hypervector, and then we have to do this inner product. But it turns out that in this inner product, we have lots of zeros, for example. But then the thing is, all the entries of the vector that I'm getting, let's say, from this front end in my FPGA, all these elements that will end up being multiplied by zeros I don't need to compute them physically. When I write my Verilog code, let's say in my FPGA, right? I can kind of remove them from the Verilog. But more than that, I can remove all the entries in this parallel computation that is taking place that will end up touching the zero, if you want. That will end up, let's say, being reduced to an element of that hypervector that will eventually be multiplied by a zero. All these entries can also be, in fact, removed from hardware. So you have to imagine an FPGA where everything works in parallel. Registers corresponding to these entries can be simply, let's say, not implemented because they will not affect the result.
And is that like sometimes like, okay, so for WKD, are you saying it would sometimes be needed, and when it's not needed, you can leave it out, but it sometimes will be needed? Is that what you're
I see
saying?
what you mean. Yeah. So of course, depending on applications, these MUCs will be different. And so in that case, if you want to build a processor that is extremely generic, that you can reprogram to get to another application, then I agree with you. You cannot afford this luxury. But if you're building a hardware that is tailored for one and only one application, and you have trained your MUC, and you have, let's say, find your MUC and you have fixed them forever, quote unquote, in that case, then when you're implementing it physically in the Verilog code, then you can remove these entries because they will eventually be multiplied by zero, and so not play a role.
But that sounds like you've just found a lower dimensional, more dense code.
Exactly.
Is that another way of looking at it? Okay. I think I get it now. Okay.
Yeah, exactly.
Thank you.
And the effective dimension is indeed D minus NZ. Yeah? So yeah, absolutely.
Yeah. Okay.
Maybe just adding a remark here. So this connection you pointed out to the random Fourier features, are you aware that there's of course also a strong connection between, you know, Tony's original FHRR code of, you know, many folds? Are you aware of that? So there's, you know, other connections have been drawn between.
Absolutely.
Yeah.
Yes, absolutely. So I'm not coming from a background of HTC, but when I was doing this work and let's say looking at the literature, in fact, more profoundly after the work, I saw that indeed a lot of links were done also with random Fourier feature mapping. But this is also something that we exploit here. And in my opinion, the original spatter code itself is not precisely replicating a random Fourier feature mapping, and that's what we try to do here. Yeah,
it's true for the non-thresholded versions. So of the you know, in the Fourier holographic reduced representations, that's very similar. But the thresholding is something that you introduce here, which is then makes it different.
Thank you.
So let's check for more questions. Rose?
Hi. So I have a really dumb question and possibly a comment, if you'd allow me the indulgence. With the, and this applies to the random Fourier features and also your your variant of that, I presume you have to scale all the input variables to have the same distributional properties. Well, I know you use a lookup table, but I mean, if you were doing the random Fourier features, I'm presuming you'd have to scale them all to have comparable standard deviations or something like that beforehand to make the sigma parameter sensible.
That's an interesting point. It's an interesting point. I will look into that. I didn't do it. So in this work, we don't do a form of which we would call the standardization, right? Yeah. Removing the mean, dividing by the sigma. Right. Yeah, we are using it as is here.
Okay. I mean, I think that's. I mean, just as a lapsed statistician, that was something that I would look at, because I mean, obviously, if you're just looking at random Fourier features, and one of your inputs was scaled in micrometers and the other was scaled in light years, then the effect of the sigma parameter on them would, you presume, be rather different.
Yeah,
so
but maybe here I can jump. It's true, I forgot to say, and I think the paper, that there's this detail here, that indeed each channel of these vectors are
Yes.
indeed mapped between 0 and 1, and then mapped into the lookup table, so between 0 and the
Yep.
maximal integer. So there is, in fact, a form of rescaling, albeit it's not a clean, removing the mean divided by the standard deviation thing, but there is a
No.
rescaling happening. Absolutely, yeah.
Yeah, but I think in general, I think that there's a lot of low-level stuff like that which has potentially an impact on the results that are seen, but which doesn't necessarily get reported very rigorously in the
True.
it just sort of gets swept under the carpet as well. Of course, we've got to do this, but
True.
it's never written down by anybody.
Yeah.
So if you'd indulge me a comment, this just gets back to what Tony and Fritz was saying. So in the and this the sparsity and your ability to effectively remove bit slices from your hardware as a consequence of that. So I mean, basically, because you're not using permutation in any of your VSA calculations, effectively you've got many one element calculations going on completely in parallel, which allows you in this case to drop some out if you know that the result's always going to be 0. But if you were to use to do anything which required permutation, then presumably you couldn't do that sparsity optimization anymore.
Also, with binding, it would be more difficult, right?
Probably,
You also
yeah.
don't use binding.
Yeah. The other thing, I'm getting back to Fritz's point about the graph showing that accuracy was initially increasing as sparsity was increasing. I wonder whether then, under those circumstances, with that interpretation of the sparsity, if you could interpret the sparsity parameter as effectively being a regularization, because presumably this is cross-test accuracy on a holdout sample.
Yes.
So the sparsity equates to effectively the number of terms in the statistical model you're fitting. So as you increase your sparsity, you're decreasing the number of terms. So you could think of it as a sort of a regularization, or maybe not. That was just off the top of my head, but
Absolutely. Yeah, we can see it as a form of L1 regularization, L0 regularization kind of thing. Yeah. Absolutely.
Okay.
Thanks a lot for your comments.
Thank you.
Very, very interesting. Yeah. Mm-hmm.
So let's see. Last chance to ask Ali question. Tony.
Yeah. One more question. Okay, so on the benefits of sparsity, if you have a very sparse code, but it's but you need to have all of your channels or dimensions present because some of them are used, are always used sometimes. Does that enable the kind of hardware you're looking at to be faster or lower power?
So you mean, if I understand you well, that if we have sparsity but we cannot remove these elements, would we have some kind of benefit? Yeah. Then the benefit will, let's say, only be reduced to the inner product in that case. So the computation that you would do in the inner product phase here will be simplified. But then in terms of area, you will not save anything because you cannot remove it from hardware. And it also impacts power, in fact, because the smaller your area, the smaller your leakage power of, for example, the chip that you design. So yeah, if you do permutations and so on, and you don't have the luxury of removing these, then its impact is less, I would say.
Yeah.
Absolutely, yeah.
Yeah, and I guess the computation here is so simple that it's not gonna, where you've just got basically an inner product of binary vectors, that it's not going to save that much. Okay, thanks.
Thank you.
All right. So I see we don't have any more questions. So Ali, thank you very much once again for the great clear talk, and thank you all for attending. So I see you all in 2 weeks from now. So have a good continuation of the day.
Thank
Thank
you.
you, Evgeny.
Bye.
Thank you, everyone.
Bye.
Bye-bye.
Thank you, guys.